Hello friends, today I am going to discuss one topic from unit number 2 from paper 7. The title of today's paper, paper 7 is plant anatomy. So under the heading of this plant anatomy paper, we are going to study two major units. First unit is organization of higher plant body and second unit is secondary structure in the plant body. So under the heading of secondary structure in the plant body, we are going to study normal secondary growth in dicotyledonous root and dicotyledonous stem. Then under the heading of abnormal secondary growth, we are going to study abnormal secondary growth in racina stem and abnormal secondary growth in bignonia stem. And last subunit under the heading of this secondary growth topic, we are going to study the structure and function of perider and lenticel. And next subunit in this topic is the study of tissue systems. Under the heading of tissue systems, we are going to study only two tissue systems, epidermal tissue system and secretory tissue system. So today I am going to discuss the normal secondary growth in dicotyledonous root. So as far as the secondary growth is concerned, secondary growth is the only important characteristic feature of dicot and gymnospermic stem and root. Secondary growth is totally absent in monocot plant. So what is the meaning of this term secondary growth? So as far as growth of the plant is concerned, there are two types of growth: primary growth and secondary growth. So primary growth of the plant takes place due to the primary meristems like shoot apex meristem and root apex meristem. So secondary growth takes place due to activity of lateral meristems. So these lateral meristems are only found in the dicotyledonous stem and root as well as in gymnospermic stem and root. Due to this, secondary growth takes place in this only dicot and gymnospermic plant. So what is the meaning of this term secondary growth? When plant attains up to some extent of growth, when few number of branches are developed, few number of leaves are developed, few number of roots are developed, at that time the original plant body is unable to develop, unable to provide the more food material. As the number of branches, number of leaves increases, the demand of the raw food material also increases. That means the increased number of leaves and increased number of branches, roots, requires more amount of the raw food material in the form of nutrients and water. And original conducting tissues which are present in the primary plant body in the form of this primary xylem and primary phloem. That means primary xylem is a conducting tissue which is responsible for conduction of mineral nutrients and water. Primary phloem tissue is responsible for conduction of food material prepared by the leaves. So if number of leaves, number of branches increases, the demand of the raw food material of the plant increases. What is the demand? Number of leaves, number of branches requires more raw food material in the form of nutrients and water. At that time, plant requires more conducting tissue. That means this original conducting tissue in the form of vascular bundles are unable to conduct the more food material. That's why when plant attains some extent of primary growth, when demand of the plant increases, what is the demand? Which demand? Demand of the raw food material in the form of nutrients and water, as well as transport of the prepared food also. So for this fulfilling the demand, in each and every dicot and gymnospermic plant root and stem, secondary growth begins. Secondary growth begins. So during secondary growth, the secondary tissues are added. So I would like to define this term secondary growth. What is the meaning of this term secondary growth? So secondary growth is nothing but increase in diameter of root and stem of dicot and gymnospermic plants. Increase in diameter due to the addition of secondary tissues in the form of secondary xylem and secondary phloem by the activity of cambium. So there are two cambiums. This vascular cambium is responsible for addition of secondary tissue in the form of secondary xylem and secondary phloem. Another cambium is also there, which is commonly known as quark cambium. So this quark cambium is responsible for addition of secondary tissue in the form of quark cells and secondary parenchyma cells. That means, as far as the definition of this secondary growth is concerned, increase in diameter of root or stem due to addition of secondary tissue in the form of secondary phloem and secondary xylem by the activity of this vascular cambium, and addition of non-vascular tissue by the activity of this quark cambium. Quark cambium. That means due to continuous addition of this secondary xylem by this cambium at the inner side and secondary phloem by this cambium at the outer side, the diameter increases, as well as due to increasing number of layers of quark. Number of quark layers also increase by the activity of this quark cambium. Quark cambium, the diameter also increases. That means this increase in diameter due to addition of secondary tissue by the activity of vascular cambium and quark cambium is commonly called as secondary growth. So secondary growth shows two steps or two stages. First stage in the secondary growth is commonly studied under the heading of vascular tissue formation. And second stage in the secondary growth can be studied under the heading of non-vascular tissue formation. So there are two steps in the process of secondary growth. So with the help of these diagrammatic figures 1, 2, 3, 4, I am going to discuss how the vascular tissue formation takes place and how the non-vascular tissue formation takes place. So this is the diagrammatic transverse section of dicot root, sunflower root. So in this dicot root, we are aware of the primary structure of this dicot root. Uppermost layer is the epidermis, it is followed by hypodermis, or it is followed by middle layer cortex, it is followed by this endodermis, then it is followed by this pericycle layer, This pericycle layer is the innermost layer and outermost layer of the conducting tissue stand. That means this pericycle encloses the conducting tissue stand in the form of xylem and phloem bundles. So in dicot as well as monocot, all roots, xylem and phloem are lying on the different radii. That means xylem lies on one radius, phloem lies on the another radius. So this arrangement of xylem and phloem bundles or vascular bundles is commonly known as radial. That means radial arrangement is an example of each and every dicot as well as monocot root as far as the arrangement of the vascular bundle is concerned. That means vascular bundles are commonly called as radial vascular bundle. So originally this type of anatomy is there: epidermis, cortex, endodermis, pericycle, phloem bundle, xylem bundle, and central region which is occupied by P. So secondary growth begins. So I have told you earlier, secondary growth takes place due to the activity of cambium. Secondary growth takes place due to the activity of cambium. So originally cambium is not there in root. It develops later on. When plant requires this addition of secondary tissue, at that time some cells below the phloem bundle. What is the name of these cells? The cells between phloem bundle and xylem bundle. This is the phloem bundle, this is the xylem bundle. Cells between xylem and phloem bundles are known as conjunctive tissue cells. What are these cells? Conjunctive tissue cells. So these conjunctive tissue cells below the phloem bundle, they become meristematic, secondarily, and forms the new strip of cambium below the phloem bundle. At the same time, this is the xylem bundle. This narrow portion of the xylem is known as protoxylem. Broader portion of xylem is known as metaxylem. So this opposite to the protoxylem, which is the layer, this layer is known as pericycle. This layer is a pericycle. So this is the continuous layer of pericycle. So this pericycle layer outside the protoxylem, the cells of the pericycle becomes meristematic, secondary. That means the conjunctive tissue cells below the phloem bundles becomes meristematic and forms how many strips of cambium? 4 strips of cambium below the phloem bundle. 1, 2, 3 and 4. At the same time, the pericycle cells opposite to the protoxylem, they again becomes secondarily meristematic and forms another 4 strips of cambium. 1, 2, 3, 4. That means total 8 strips of cambium are developed. 4 strips are developed from pericycle opposite to the protoxylem and 4 strips are developed below the phloem bundle from which tissue? Conjunctive tissue. That means tissue which is located in between phloem xylem bundle is known as conjunctive tissue. That means from pericycle and conjunctive tissue, total 8 strips of the cambium are developed. So these cambium strips grows laterally. So this strip when grows laterally, it joins with this strip. When this strip joins laterally, it joins with this strip. That means this total 8 strips due to lateral growth, they join with one another and forms the wavy band of cambium. What is the name of this cambium band? With the help of this yellow chalk, I have shown the wavy band of cambium. So this wavy band of cambium is developed due to joining of these 8 strips of the cambium. So activity of this wavy band of cambium is uneven. What is the activity? Cell division activity. That means cell division activity of cambium below the phloem bundle is more as compared to the cambium which is lying opposite to the xylem bundles. That means due to more activity, cell division activity of this cambium band below the phloem bundle, the primary phloem bundle, this green patch is the primary phloem. This primary phloem bundle is pushed towards the periphery. And at the same time, the activity of cambium is very less in this region. That's why these 4 strips of the cambium, due to more activity, the cambium becomes circular. Due to uneven activity of cambium band, wavy band of cambium becomes the circular. So when circular band of cambium develops, the cell division activity of cambium becomes even. That means at all points, at all regions, the circular band of cambium shows same or equal cell division activity. So what is the activity of this cambium? So this cambium cells divides tangentially and produces the secondary tissue. So at the inner layer of the cambium redivides tangentially and produces the secondary xylem cells. At the same time, the outer layer of the cambium cells divides tangentially and produces the secondary layer. That means this vascular cambium is responsible for addition of secondary xylem at its inner side and addition of secondary phloem at its outer side. That means constantly this cambium take part in addition of secondary tissue in the form of secondary xylem and secondary phloem at the inner side and outer side. So year after year, when this cambium is taking part in addition of secondary tissue in the form of secondary xylem and secondary phloem, obviously the diameter of this root increases. That means this is the one reason for increasing diameter of the root, addition of secondary tissue by the activity of this cambium in the form of secondary xylem at inner side and secondary phloem at the outer side. So when secondary phloem is produced by this cambium, the primary phloem is pushed towards the cortex or towards the periphery. At the same time, what is this? Primary xylem. 1, 2, 3, 4. 4 radiating rings of the primary phloem, primary xylem. So this primary xylem is pushed towards the center. What is the central region? Central region of the root is occupied by this pith. So this pith region undergoes disintegration, or cells of the pith are crushed and place of the pith is taken by this primary xylem. That means after secondary growth, this primary xylem is showing star-like appearance. That means these 4 reeds of xylem, they occupy the pith region. With region is occupied by this primary xylem. Then this radiating rows of cells, elongated cells, are produced from this primary xylem. They are known as medullary rays. That means medullary rays. That means this primary phloem is pushed towards the periphery, primary xylem is pushed towards the center, and it acts, it shows as like the star-like appearance or four radiating rings. When this cambium is responsible for addition of secondary xylem, secondary phloem. So due to addition of secondary xylem and secondary phloem at the central portion, what happens? Which is the outermost protective covering of the root? Epidermis. So epidermis comes under stress. Epidermis comes under stress due to addition of secondary tissue at the central region, and epidermis ruptures. When epidermis ruptures, what will happen? There is a possibility of entry of pathogens like bacteria, viruses, or nematodes, etc. into the inner tissues of the root, and it may damage the tissue. In order to protect the inner tissues from entry of pathogens like bacteria, viruses, etc., root requires another protective layer. At that time, the cells of the pericycle, which is the layer enclosing the conducting tissue strand, known as pericycle. So cells of the pericycle becomes meristematic and forms the another cambium, which is known as quark cambium. So this quark cambium, origin of quark cambium is from pericycle from root. So this quark cambium is showing similar activity as like this vascular cambium, and cells of this quark cambium divides tangentially, and at the peripheral side it gives the quark cell layers. That means the layers of the quark are thick and sugarized, dead tissue layers. That means this rectangular brick shape empty cells are developed at the peripheral side. These are known as quark layers. At the same time, the quark cambium produces at its inner side the thin-walled parenchyma cells. They are commonly called as secondary pericycle cells. That means this three-layered zone of cells, secondary pericycle cell, quark cambium, and quark cells, constitutes the perider. So this perider is the outermost protective layer. That means after secondary growth, due to activity of this quark cambium, the periderm formation takes place. So epidermis, outermost covering of root, is replaced by this periderm. So periderm formation is nothing but non-muscular tissue formation. That means in the course of the secondary growth of each and every dicot root as well as stem, there are two events. First event is vascular tissue formation, which takes place due to the activity of this vascular cambium, and it adds secondary xylem at the inner side and secondary phloem at the outer side. It is responsible for increase in diameter. At the same time, when epidermis ruptures, epidermis requires another protective layer. At that time, the pericycle cells become secondarily meristematic and give rise to quark cambium. This quark cambium produces quark cells at the outer side, and secondary parenchyma cells or secondary pericycle cells at the inner sides, and these three zones of cells produced by this quark cambium constitutes the periderm. This is nothing but the non-muscular tissue formation. So as like this, stem also shows these two steps: muscular tissue formation and non-muscular tissue formation during the course of secondary growth. So that's all about this, our first article from botany paper 8, plant anatomy syllabus. So next time we shall see the normal secondary growth in dichotomous stem.